For Unit 6, Lesson 2, we will be discussing potential energy diagrams. The heat of the reaction, or delta H, is the measure of our energy change during our chemical change. Whenever we form products, we must break the bonds in the reactants. Breaking bonds requires energy. When we form new bonds in our products, energy is given off. The difference is our delta H. Exothermic reactions give off more energy. Our delta H is negative for these reactions. This means it requires less energy to break our bonds, and we're giving off more energy when we form bonds. Endothermic reactions take in more energy to break the bonds. Our delta H is positive for these. To show the changes in energy of a reaction over time, we draw potential energy diagrams. This maps out how the energy changes as our reactants get converted to products. This is the general shape for an exothermic reaction's potential energy diagram. We start with our reactants on the left, higher in energy. The top of the hill, we call that an activated complex. This is a very temporary, unstable arrangement of atoms that forms before our products. And finally, we have our products in the bottom right. We can make two other measurements with these diagrams. One is our activation energy, the energy needed to start our reaction. To calculate this value, we subtract the energy of the activated complex from our reactants. The other value we can determine is the heat of the reaction. To get this, we take the products minus the reactants. This is a general pattern for an endothermic reaction's potential energy diagram. Noticing now our reactants start at a lower energy, our activated complex is still at the top of the hill, and our products on the right but higher in energy. Our activation energy and delta H are calculated using the same equations as before. For example number 1, we are first asked to identify the energy of the reactants, products, and activated complex. Reactants are located on the left with an energy of 100, activated complex at the top with an energy of 400, and our products on the far right with an energy of 300. Next, we need to calculate our activation energy, which, if you remember, is the difference between our activated complex and our reactants. So we take 400 minus 100 to get 300 joules. Our delta H is our difference between our products and our reactants. We would subtract 300 from 100 to get 200 joules. And our final question asks us to identify what type of reaction is shown in this energy diagram. The overall pattern of having the reactants lower in energy and the products in higher in energy makes it an endothermic reaction. We can also tell this from our delta H being positive as well. Almost every reaction is reversible. Let's try the same example but in reverse, meaning our reactants and products switch places. Identifying the energy of our reactants, products, and activated complex. Our reactants are now on the far right with an energy of 300. Our products are on the far left now with an energy of 100, and our activated complex did not change. It still has an energy of 400. Calculate our activation energy and delta H using the same equations we have before. To get our activation energy, we take our activated complex of 400 minus our reactants at 300 to get 100 joules. Our delta H, we're taking our products minus our reactants. Our products are at 100, subtracting from 300 to get negative 200. And lastly, identifying what type of reaction the reverse is. Our reactants start higher and our products go lower. In reverse, it's an exothermic reaction. It's always going to be opposite in reverse. Pause the video and see if you can do example 2 on your own. Again, pause the video and try the reverse of example number 2. The speed of a reaction is dependent on the activation energy. The smaller the activation energy, the faster the reaction will occur. If you remember, a catalyst speeds up a reaction by lowering the activation energy. Our potential energy diagram would show a smaller hill with a reaction with a catalyst.